Welcome back. Today we cover vectors. Hopefully you're finishing up project 8. It's due next class. Also want to point out that required form number 3 is coming up due soon, so have a look at your calendar to know the exact dates. Let's get started with the class notes. Many quantities involve a magnitude and a direction. In physics, these include displacements, forces, and magnetic fields. Other uses occur in economics, computer graphics, and higher math courses. These quantities can be represented by vectors, a mathematical object, often represented by an arrow, incorporating both magnitude, which is the length of the arrow, and direction, which way the arrow points. So just as a quick example here, I could tell you that my speed is 55 miles per hour, and that's just a straight number with a unit at the end of it. But if I wanted to give you a vector, then I could tell you my velocity is 55 miles per hour east. So that 55 is the magnitude, but the east is the direction. And so those two pieces of information together comprise the vector. So again, 55 miles per hour is just a straight number. Scalar is what we're going to call it in a second. But if I say 55 miles per hour east, that has a magnitude and a direction, and we call that a vector. 2, a vector is written as a variable with an arrow over it to distinguish it from a scalar, which is basically a fancy word for an ordinary number. So let's start putting all this stuff to use in number 3. Suppose Sandy is in the math studio and is considering moving a chair to another location. Let's put the chair on a set of coordinate axes and assume the chair starts at the origin. Sandy first moves the chair diagonally 2 feet east and 4 feet south. Then Sandy moves the chair diagonally again 6 feet west and 4 feet north. Let's draw vectors, V and W with little arrows on top of them. That's our notation for vector. For each of Sandy's movements, as well as a vector for the net movement. Net just means total. So we're going to start the chair at the origin. So we'll put it there. And then we're going 2 feet east and 4 feet south. So that'll be the first direction. So we start at the origin, and then we go 4 feet east. So 1, 2, 3, and 4 feet east. And then that is not right. 2 feet east, 1, 2, and then 4 feet south, 1, 2, 3, 4. And so the chair is going to end up here, and I'm going to draw a straight line connecting those 2 points, and I'm going to put an arrow on that line segment to make sure that we're clear which direction we were going, because the chair could just as well have started here and gone the other way if I didn't put the arrow on it. So starting at the origin and then going that way. So we put the arrow. And then we're going to move the chair from this current location. We're going to go 6 feet west. So 1, 2, 3, 4, 5, 6. And then 4 feet north. 1, 2, 3, and 4 puts me there. And so then we're going to draw an arrow in that direction. Let's do a little bit better. I'll make sure that it hits the point and then the arrow. Okay, so this purple thing is, I guess, what we're calling V with an arrow on top of it. So vector V, and then W is the red guy, the red vector. And then we want another vector for the net movement. In other words, what could Sandy have done if she wanted to be more efficient? Because she kind of did some extra moving around here. If she wanted to start here and end up over there, probably would have been better off just doing a straight shot to the left. So the net movement in our case is the sum of V and W, which apparently is just 4 places to the left. So in this case, I could say it's just 4 feet west and nothing north or south. All right, so those are 3 vectors in the picture. 4, the sum of 2 vectors is called the resultant of the 2 vectors. Our diagram illustrates the tail to head method. So some vocabulary you'll find in the book, but the tail of the vector is this guy out here, and the head of the vector is where the, that arrow is. So the tail to head idea says if you want to take this vector and add this vector, what you should do is draw this guy until you end up at the head of that vector, and then from there draw the tail of the other guy. And then when all is said and done, you start with the tail of the first thing and end at the head of the second thing, tail to head. 5, we can also multiply a vector by a scalar, which is just a number. For the vector v shown, draw each of the following vectors. All right, so in this picture we have vector v, which apparently is 2 east and 3 north. And what we're going to do is, in part A, draw the vector 2 times v. So all we're going to do is double this vector here. So instead of going 2 feet to the east, we're going to double that and end up 4 feet east. So I'll put a little dot here temporarily. And then instead of going 3 north, we're going to double that too and go 6 north. So we'll put a dot up here temporarily. And then we're just going to find the spot where these dots kind of meet. And so this is the end of the vector. And actually it should be exactly, we should notice that it's exactly the same direction, same angle as the original vector. And it's exactly twice as long as the original vector. Let's take a look at B, which is a 0.5v. So I'll just circle this guy in green so we know that's the green one. And then we'll do 0.5v in purple. So it's going to be the same vector as the original black vector that's drawn on this picture, but we only want to go half as long. So I think that ends me right there, half as long. And then finally, let's do in blue negative v. So negative just means opposite, right? So instead of going 2 east, we're going to go 2 west. And instead of going 3 north, we go 3 south. So let's draw this one in blue. So 2 east and 3 south, I think, lands me right there. So hopefully we see that negative v is just the same as the original black vector v, but just going in the opposite direction. 6. Vectors can also be described by breaking them into components. These are the vector equivalent of rectangular coordinates. And so what we saw up above in this picture, basically the stuff with the directions here. Where is it? Right up here. Here are components. 2 feet east and 4 feet south. Those are rectangular coordinates, right? It just says from here you go 2 that way and 4 that way. And so those are called the components. 2 is the x component and negative 4 is the y component. A unit vector is a vector of length 1, kind of like a unit circle was a circle of radius 1. We denote the unit vector in the x direction as I, and the unit vector in the y direction as j. So for example, that right there is the vector I, and this vector right here is the vector j, just pointing in the positive x and y directions respectively, and having a length of 1. So those are our 2 unit vectors, and we call them I and j. It's a little bit unfortunate. We've just recently started thinking about imaginary numbers, and we use I as the kind of basis for the imaginary numbers. That really doesn't have anything to do with the I that we've got here. So it's unfortunate that we use the same letter, but that's what we do. Then any vector can be expressed in terms of I and j. So for example, vector v from this picture right here. Let's see, vector v said we were supposed to end up at this spot right here, right? So that was 2 to the right and 3 up. So 2 to the right is just 2i, and then 3 up is 3j, and all we do is add these guys together, and that's our way of saying go 2 to the right and 3 up. All right, so that vector right there, v, is 2i plus 3j. If the x-axis points east and the y-axis points north, represent each of the following movements in terms of I and j. This will be a good time to pause the video, see if you can write your answers to each of these problems. If you're really not sure what's going on here, we'll do the first one together. Walking 2 miles east, that's 2 in the positive x direction, so that's 2i. So pause the video, see if you can come back after you've done these 4. Okay, 3 miles north, that's 3j. 2 miles east and 3 miles north, that's just adding the answers to the previous problems. 2 miles east and 3 miles south, so there's your 2 east, but now south is down, so that must be minus 3j. And then 5 miles northwest, which means perfectly between north and west. Okay, so this one is trickier because telling me that we've traveled 5 miles at an angle doesn't tell me exactly how far we've gone in each of the x and y directions. So we know that we're out here 45 degrees and we've traveled a distance of 5, but I don't know, how do we find that number right there? Now, how do we find that number right there? Okay, well, we know it's a right triangle, so we could use, sine or cosine or tangent. In this case, it's a 45, 45, 90, so we don't have to get into all that. But we know that if the sides of your 45, 45, 90 triangle, 45 here, that you can call it x, and x root 2. So apparently x root 2 is 5 in this case. That's the hypotenuse. So that means that x is 5 over root 2. And so let's get a decimal approximation for that number. So apparently we're going about 3.5 in the x and y direction. Okay, so this one is, if you want the exact answer, it's 5 over root 2i plus 5 over root 2j. Because it's that perfectly 45-degree one, we know it's the same. And then that's approximately 3.5355i, and then the same thing for the j. Okay, we can use the trig we used for the last example to resolve any vector into components. This will be key in physics. All right, so we actually kind of short-circuited the trig in the last one just because it was a 45-degree one, but we won't be able to do that here in 9, so let's give 9 a shot. A disabled automobile is pulled by means of ropes subjected to the two forces as shown. Kn means kilonewton. It's a unit of force. Find a single force that is equivalent to the two forces together. Begin by resolving each vector into components. All right, so we've got this car that, maybe it's in a ditch. It can't move on its own. And so it's being pulled by a machine or a strong person that direction, and then a machine or a strong person that direction. Kn, again, is a unit of force, so it gives you a sense of how strong the pull is in each of these two directions. So apparently this machine is twice as strong as that one because that's 2 kilonewtons and that one's 4. And the angles are close but not exactly the same. So I guess this B vector is pulling a little bit more up and a little bit less to the right compared to this vector down here, which is pulling to the right and down, but a little bit the downward pull on this one isn't quite as big as the upward pull on the 30. Okay, so just to be clear, yeah, the car is going to start moving. I guess is it going to start, let's see, is it going to go directly to the right when we pull? Well, this angle of 30 is more than the 25, so that means that it should angle up a little bit higher than normal if these guys were pulling with equal forces. But I think it's actually going to end up angling even more towards this guy because he's twice as strong as this one here. So the question is what's really going on here? What is this equivalent to? If we could just replace these two machines or these two people with one stronger machine or one person, then what would it be? So that's the goal. Okay, so what we're going to do is we're going to first break the vectors up into components. So for example, if I want to take a look at, let's see, so we can call this guy here vector u, and let's start with vector u. Okay, so we know that vector u is something times I plus something else times j. And so the question is, how much of this vector right here is pulling in the x direction? Well, what we need to do is just go straight down and figure out what this length is right here, because that's how much we're going in the x direction. All right, so that's what we want to find. And in order to find that, well, we know that the trigonometry is involved here. So we've got the hypotenuse is 4 long, that's this guy. And so maybe we'll label that as a 4. That's the length of that hypotenuse. And which trig function do we want to use? Well, let's see. We have 30. We want the adjacent side, and we know the hypotenuse, so that feels like cosine. So if we wanted to do cosine of 30, I'll put this, then I'll erase it. So cosine of 30 is equal to the adjacent side, which is the purple, divided by the hypotenuse, which is 4. So that means that the purple question mark is really 4 cosine of 30. So that's what we're going to put up here. Okay, so we've got that, and then we can play the same game to find the vertical component, the j component. So I'll do that here in black. This is what we're interested in knowing the length of. And so it's the same idea but sine. So right up here, we're going to put 4 sine of 30. Okay, so let's get both of these guys. Now, one of them is kind of a nice number, right? Sine of 30 is a half. So that part's easy. Cosine of 30, you guys know it as a radical. I guess it's root 3 over 2. But we're going to get decimals anyway, so let's just get decimals. So what are we doing? 4 cosine of 30. Don't forget what mode you're in. We'll get that decimal, and we'll be really silly and type this in, even though we know sine of 30 is a half, so that should be 2. Okay, so those are our components. So that means that vector u with the arrow over it, is approximately, what did we have here? 3.464i plus 2j. Okay, and then we'll play the same game for the other vector, which I'm going to call v. And so it's exactly the same thing. So we'll just jump to the punchline here. V is equal to what? 2 times cosine of 25 with an I on it, plus 2 sine of 25 with a j. And in fact, this whole idea of multiply r by cosine and r by sine, we saw it when we were doing trig. We saw it again when we were doing polar coordinates. We saw it again when we were doing imaginary numbers. So, so that's it. But here's the problem. The problem is that both of these numbers are going to be positive, whereas I know that this machine down here is pulling to the right positively, but it's also pulling down, which better be a negative. So, I mean, if you want, I guess you could just change that to a minus sign, but that doesn't seem very clean. It seems kind of risky, actually, that you might forget it. Well, that 25 degrees isn't really 25 degrees in standard position, right? If we put our axes here, then we would say this is really negative 25 degrees. So that feels to me like a reliable way to do this, is put some axes wherever is natural, and then make sure you use the version of the angle that is in standard position. Okay, so let's try this now and see what we get. So here we're going to do 2 cosine of negative 25, fully expecting a positive answer. Okay, that looks good. And then 2 sine of negative 25, expecting a negative answer. All right, both good. So let's put that down here. So V is approximately 1.8126i minus 0.8452 minus all kinds of troubles, minus 0.8452j. Okay, and so if we want the net force, the total force, all we do is add these guys together. So U plus V. And so we're just going to copy these two things on the same line. 3.464I plus 2J, and then I'll just put the V part right below it. V is 1.8126I minus 0.8452J. And then we're just going to total these guys up, and whatever we get will be our answer. So let's do that here. So first I'll add 2 to this number. We get that. And then the other one, okay. So 5.2766I plus 1.1548, we'll say. Okay. So when all is said and done, essentially these two machines working together pull about 5 units to the right and about 1 unit up, which seems reasonable given the green thing that I wrote in here. That was just kind of my guess as to what these machines were really doing. So in theory, the car would follow the green path. If you turn these machines on at exactly the same moment, the car would follow the green path as if it were being pulled by a machine right here. And it would just be, 5 and change to the right and 1 and change up. And I'll draw one more thing into this picture. Really what I should have done was copy this red vector right here, but copy it starting here. This is the tail to head idea. And whatever I get, if I just copy that red vector perfectly, then the green thing really should have gone from there to there. So that's the sum of the two vectors. Okay, so this whole idea of components is really important in physics. So hopefully this component thing made sense. Okay, so let's go to the next page before I break this thing. Okay, 10, some notation and one last theorem before you do the activity. To denote the magnitude or length of vector v, we write, it's basically like absolute value, but we actually use two of them, so it's like a double absolute value around the vector. In physics class, you may see different notation. Bold v refers to a vector, and unbold v refers to the length. No, we don't make use of that like when I write stuff down because I can't write things in bold. But if you see it in a book, just know that bold means vector. Okay, so then we've got this nice theorem here that says that if you want to take a vector and just write it in component form, and I know it's component form because I see my I and my j, then you take the magnitude or length of the vector, multiply by cosine of that angle, and then separately the length of the vector times the sine of the angle. That's exactly what we did, right? In the first problem, it was 4 cosine of 30 plus 4 sine of 30. Why was it 4? Because 4 was the length of that top vector. And then in the second problem, it became 2, length of that vector. Okay, so I'll make a video for the activity, but give it a shot before you look for the video.